Kavita madam, please begin.
Faculties have joined, sir.
Madam, please start the session. We are live on Facebook.
Okay, sir. Good afternoon, dear sir. Good afternoon to all respected heads and our faculty members. Thank you, sir, for taking out your valuable time for us today. So today with us, we have our guest speaker, Mr. Mukesh Lal Chandani, the General Manager of Atlas Copco Company. This company deals with the manufacturing of various kinds of air compressors and several other industrial equipments. Now, talking about today's guest of honor, he has earned his degree of master's in technology with specialization in the subject of machine design from IIT Roorkee. He has a vast experience of more than 28 years in the field of static equipment, piping, and engineering services. He has been instrumental in 1500 PSI recip compressors designing. He was deputed in Belgium as program lead for the development of the product. Since last several years, he is managing engineering teams and building digital competency in Global Engineering Center of Atlas Copco Company as the general manager. Now, I request sir to exchange his expertise on today's topic of the webinar in digital twin for industries. Over to you, sir.
Thank you, Kavita madam. It's really honor to be here and present on the digital twin, close to what today's talk about when we talk of the digitalization. So I'm really happy to share my thoughts here. Let me start sharing the screen and a small presentation. Feel free to ask questions if any comes now or later. I should be able to help you with the questions here. Let me know if my screen is visible.
Yes.
Okay. Kavita madam has explained about our group. Let me also take here a few moments to make you familiarize with what Atlas Copco is about. So we deal with various industrial equipments, mainly Compressor Technique, which deals with compressors. These ranges from 2 kilowatt to 2 megawatt compressors. So these are, and also various technologies we use, right from piston compressor to screw, oil injected screws, oil-free screws, or scroll pump, and various other technologies. We also support here medical gas solution, which was very much prominent in the time of COVID. And we have also the other technology team, which is Vacuum Technique, which deals with scientific vacuum, industrial vacuums, which are mainly used for making semiconductors or collecting the noble gases, which actually liquefies at minus 196 degrees centigrade or even lower than that. So these are the vacuum pumps or industry equipments that we manufacture under Vacuum Technique business area. We also have a business area which is on Industrial Technique, which deals with tools and technology for tools mainly for assembly techniques. This is basically into various industry we use for automotive assembly, for even smaller components assembly, doing also the detailing in terms of when you do the assembly, you also need to record a lot of data. So these are the smart tools which are used in today's smart industry solutions. And then last but not the least, we have also Power Technique business area, which deals with mainly equipments which are mobile compressors, lighting towers, generators, and also pumps. So these are the equipments which are used in the construction industry. So our division is Global Engineering Center, which is part of the Compressor Technique, but we serve for Atlas Copco globally, worldwide, and we have team in the mechanical engineering, electrical, and digital, manufacturing, and related competences. So going forward, small glimpse about the size of the company. So we are present in more than 180 countries. Employee base of 43,000 employees in 70 countries where we have production as well as distribution channels. This company was established in 1873. So we are having 1 year. Next year we will be celebrating 150 years. So this year we are celebrating 149. We have turnover of 11 billion euro and operating margin of 21.2. This is very important to explain that, okay, the company puts a lot of efforts in various industry segments, and that you can see also in the picture here. So today's topic is on the digital twin. But first of all, if we want to understand a digital twin, I would like to show you a small video to make you familiarize. Most of you might be familiar, but this will give you a good connect. What are we talking about on digital twin and why this is very important in today's world, and how physics and mathematics plays an important role for making this realized. I'll play the video here. So digital twin is nothing but replica of physical asset into the digital world. Why do we want to see digital twin? If you are familiar with, data is new oil. That's what people are saying. Why it is new oil? Because like the fuel which gives boost to our economy, data is going to also give boost to our economy. And a lot of companies are now going forward to the data-driven decision making. That means you actually do the decision making not with your gut feeling, but also with some amount of data available, and based on that you can take the decision. And accordingly, if we talk about, it's also about how realistic will my decision be, how close to reality am I going to take the decision. So these are the challenges which today's management or today's designer or calculation engineers are facing, and that's where this is going to be a crucial one. So it's all about getting insights of the product's performance, and it's not only into the industry or a mechanical industry or electrical industry or any other place, but it can be applied into virtually any field. You've also seen in the video for healthcare industry or for utilities industry. Even in the smart city also, this is going to be the main solution, where you get more and more update about digital twin, or more and more insight about how the things are performing. So it is to get the better insight on the product performance. And this also helps us to get better inputs for optimum performance. If I had to optimize some of the product, I need to understand how things are performing in the field, and which are my variables, design variables that are impacting on the performance. So that is also evaluated from a different perspective, and that brings more reliability and efficiency in the products. Yeah. So this is very crucial to understand from the physical part into the digital twin. Yeah. So this, when we say this is a digital twin, it is based upon how many data points are collected, from which all background you collect the data and put it into the data base or data lakes or data structures, and then put the algorithm, which is either white box or black box, and then you can create the simulation that how it is going to perform. Yeah. I'm going to explain you a little bit more into digital twin. Yeah. And then we will also talk about role of physics and mathematics into it. So before that, I'll give you a very small example here. Yeah. Let's understand, if we talk about a windmill or wind turbine. So we know that this is a very big equipment, and it generates power based on the wind pressure and wind directions. So there are a lot of sensors added to it, and also there are a lot of actuators. Now, sensors will give the signal to actuator whether it has to function or not, but it also will transmit the data back to a digital twin world of this replica of this wind turbine in the digital replica. Now, what happens when the sensors provide this data? And if based on the data we have modeled or prepared the mathematical model that how the particular performance in terms of power generation or in terms of stresses at different places will come into picture. So then this computer model will also use this data, use the machine learning, which I'll also talk in the further slides, and can create the output in terms of the alarms and diagnosis. So alarms may be that, okay, look, the wind pressure is going very high, probably wind direction is not the right. So those kind of alarms and diagnosis it can create. And also prognosis, that what if, in case if, let's say, we have to simulate that what if I put up a higher gear ratio, will it create more power or will it create less stresses? So those kind of things also can be analyzed with those mathematical modeling. And then when you couple it with the uncertainty, because we know that when we manufacture any of the two components, they might not have the same tolerances, and this brings more of the uncertainty. So those kind of uncertainties, when we put it in on top of the physical model or mathematical model, then it can also give us more detailed view that what could improve, what type of sensors can we use, which location is best for the actuators. So all such things happen with the digital twin. Yeah, it is to analyze things far ahead of the real life scenario. Some of the examples on the very high tech is, you might be knowing this Tesla cars, automated driving cars. It's also part of the digital twin when it actually mimics the behavior or the pattern at the road, and then takes the decision that at what speed, at what direction the things or the car or automotive vehicle has to move. So those kind of things play a very important role. So physical principles with mathematical modeling on top of that creates the better understanding and visualization that what will work, what will not work. Yeah, this is as simple as that in terms of digital twin on a simple product. Now, let me bring you to how we at Atlas Copco are using. So our compressor looks like something like this. Yeah? A very simple way to understand is, let's say a car is there, and then in a car there is an engine, right? So similarly, in a compressor, there will always be an element. Now, this element is nothing but engine to the car. So if we prepare a digital twin of this kind of compressor, then we need to also make the mathematical modeling of each and every module. Yeah. One of the module is, let's say, on the core element, where the core framework, if I talk about the expectation from a calculation engine, it says, I want to find optimum gear ratios and element sizing. So what could be the best size for that kind of performance? And this is normally a performance curve. What you see a dark or different colors on the curve is basically the different data points on the curve that we had taken in the labo, and then we could put forward the right mathematical model, or could be a cubic or equation, which actually helps us to identify that, okay, what could be the right way. And then we know that, okay, the particular performance curve has higher dependency in terms of pressure drop or speed, and also on the different kind of environmental parameters like atmospheric pressure, atmospheric temperature, or oil pressure, oil temperature. So if we actually put forward those parameters in the mathematical modeling, we can actually mimic the behavior of any of the compressor well before it is put into the practice. So that's where the calculation engineer would like to know that, okay, how is my gear ratio going to work? Or in terms of that, if I have kept this much tolerance, how is it going to behave in the field? So this is where the complexity plays into picture. Then similarly, on the controller side, if I talk about, this is nothing but on the vehicle also, you have a lot of, on the dashboard, you have a lot of controls, or you actually have output device, which shows the different parameters of the engine, how much is running speed or engine speed, RPM, and so on and so forth. Similarly, here also we have the controller, which actually gives a lot of insights about what is the operating pressure and RPM of the machine, and also some of the set parameters. So there also, if control engineers is there, he or she would like to know what could be the effect of different control strategy so as to optimize the power. So those kind of things can come forward from the digital twin modeling. Yeah. Similarly, if we talk about the frame, or the part which is hosting our entire equipment, then there also it is very important to know how is the vibration going to play, where do I need to put my supports. So those kind of physical framework, what we are seeing here, if a calculation engineer might have the interest to know that, okay, how is dynamic behavior of my system. Yeah. So those kind of thing also can be predicted based on the data analysis, based on the vibration analysis at a different place. Now, all this comes into a small different modules, and these modules, when they work together, they actually can provide right insight for the next design to work, but also it can give the right insight for service engineer, whether the particular equipment is in order or it is really out of order. So if we little bit zoom in the life cycle on the machine, then we have one of the important parameter is design. So how do I do my next design in the right way? Or how is my manufacturing going to happen? So different tolerances will have different impact on the performance curve. So is it really good to keep too tight tolerance, too relaxed tolerance? So those kind of thing also comes into the picture from the manufacturing capability point of view. Then the third one is the assembly. Where do I need to do the assembly right, or where do I need to measure the right torque and other things? So that happens with the assembly. Give me a minute. So that happens with the right assembly process. But even this also can feed in data back to the system for the particular machine which is assembled, to know that, okay, how it is going to perform in the field. Similarly, on the installation, so what tolerances or what alignment has been made during the installation, And last but not the least is service. So how is the service going to happen on such equipment? So all this important phases in the product life cycle, if we see, then at every stage, there is the model that has to be prepared, and this algorithm has to take the input from the central database system, where different data is coming into picture, but also it will have to feed in data back to that system so that the next module can also work very well. For example, if in a machine shop, if one of the element is out of tolerance and that particular thing has been mimicked back into the system, when the same particular element comes into the service, it can correlate that, okay, what would happen if my tolerances were out of limit? Is it still going to work well or not? So this is something which gives you the clear picture or 360-degree picture of the machine which is designed and put into the field. Now, if I really go into the digital twin part of it, then we have a digital twin database, which also we call it as model-based engineering. So if you see here, the arrow shows from both the directions, the data is exchanged. And then it can also be used by the modules which are prepared around these different steps. And these modules can then, I would say, improvise their own model in terms of model-based engineering, in terms of the errors, in terms of data sets which has to be used, so that it can create the right or it can perfect the model going forward, so we can have more reliable solutions in the future. With help of this, the advantage that the organizations get is optimum design in terms of design or energy efficiency, which is also required by the UN now in terms of environmental goals. Then we have better process capability. So we know that, okay, what type of machines are required, what process capability are we should we be targeting, so as to have the better manufacturing. At the end, also improved quality control in terms of assembly and final product. When it goes into the installation, we also can help our service engineers, site engineers, to do the installation right and quick installation with the right level of alignment that is needed at site. And finally, the talk which is happening because of digital twin is predictive and prescriptive maintenance. This ensures higher uptime, higher reliability, and then also the better efficiency on the products. Yeah. So this is basically the complete cycle on the digital twin that you can see from different perspectives, how it is used. But now let's also talk about how the digital twin modeling works. So if we talk about digital twin models, normally it is in two ways we actually can do the modeling: A, white box, and B, black box. So what is white box? So white box is basically where you know that the system is behaving perfectly on the physics principles, and there is no case of uncertainty, or very minimal uncertainty comes in case of the physical laws when it creates. Like example, if I talk about how much is the bearing load coming on the shaft. So we know that, okay, if the shaft is carrying so much of power and so much of diameter is of the shaft, we also can estimate, okay, what could be the bearing load in terms of bearing stress, or in terms of contact stresses on the bearing, but also the performance curves. So those are the formula-based calculations, and there is very minimal amount of uncertainty that comes, or I would say inaccuracies. So this is, let's say, 90-95% is the science or physics or mathematical based model. However, also in reality, it is not possible to have 100% accurate model according to physics, because there could be some amount of uncertainties or inaccuracies into the manufacturing, and that leads to non-compliance to the theoretical or physical knowledge. And that's where things also can be perfected with help of data points. Yeah. Exactly opposite is black box model. So black box model works on the fully on data, and no prior knowledge of physics or theoretical analysis is needed. However, what is most important here is statistical analysis, and it works completely on statistics. So artificial intelligence or neural network, that is example of black box model, because in the neural network, they use several different principles, which actually then defines that how the data is moving around. So it is like cluster of data is given to you, and then need to find out what is the best path that a model is following using that data point. Are they really showing you some pattern? And it becomes more complex when you have many variables on which a data point is dependent. For example, if I talk about the performance curve generation, yeah, it's following the mathematical modeling. However, still there are a lot of variables. So it has got variables like inlet pressure, inlet temperature, atmospheric pressure, relative humidity, oil temperature, speed of the shaft. So these are all the inputs for the performance parameters. Now we need to find out sensitivity of one or other parameter on the model. So there, artificial intelligence or neural network can find the right pattern and can tell us that which element, which particular parameter is more sensitive than others. And this can help build the right model for the performance curves. So, but in industry, we never go with either fully white box or fully black box. It is somewhere around the gray box, because we know that, okay, in both the cases, our reliability is reliability is of very high importance. So we need to make sure that whatever decisions we take is with the high reliability. So fully statistical model also can be very fragile, and bigger data sets are required to make sure that higher probability or higher reliability is achieved. So this is basically the way now when we talk about a white box model or black box model, how these digital twin models are prepared. Yeah, I'm not sure if we will be seeing questions here, but I guess this is webinar, so maybe there will not be any questions right now. Am I correct, Kavita madam?
Yes, sir.
Okay, so let me move to the next slide. So this is an example here. So this is again the example from the industry where if I talk about the element which is engine is to car, so element is to compressor. So if I talk about that, and if we just explode the entire view, then there are several components, those are assembled. And for each of this, the right data point which comes and sits into the digital twin database is like, it's a bill of material. So are we using the right bill of material? And then for a particular serial number, we also can understand that, okay, what kind of component has been used. Then what has been the machining input. So the profiles are very crucial, which is actually creating the pressure or generating the pressure. So then there are microns of tolerances on this. So the entire profile, we also can see that, okay, how impactful is this profile on the performance. Then in the manufacturing, we can also see from the process capability that, okay, is this really capable of the processes? Then even from the machining data. So the first element, we know that, okay, it can get manufactured very clearly, but then if the tool wears out, then the impact also comes onto the machining or manufacturing. So the machine data, whether the tool wear out has been seen, or at what instance in the batch the particular component was manufactured. Now, all these data actually helps us to improvise our manufacturing, improvise our delivery and efficiency. And then this also requires in-depth knowledge on the statistical analysis, in-depth knowledge on the pattern analysis. If I talk about here also, the correlation is required that, okay, where the data point, if that goes out of the limit, it impacts onto the performance. And finally, the performance characteristic here. So also, this is as modeled. So around this, when we plot the data points, we can come to know that really the mathematical model is following on the data points that are measured, or are there any correction required into the mathematical model? So that's how we actually use digital twin to make sure that our elements are meeting the efficiency criteria, and our manufacturing processes are also complying to the demand which is from the industry 4.0. So that was until this slide was how do we use in digital twin, and what does it make, what does it require to prepare the complete model and all. But let me also bring you to the next topic, which is when we talk about such digital twin, what are the different tools that are required to create digital twin? Yeah, of course, the first thing, these are tools, but the first and foremost thing is the algorithms that needs to be defined, the mathematical model that needs to be defined. So their domain knowledge is very important. So if we are from the mechanical domain or electrical domain, the domain knowledge is very important to put forward the competency into the model, whether it is white box, whether it is black box, and so on and so forth. The second important competence that is required is mathematical modeling itself. So how are the correlations going to work? If we talk about the performance curve, what kind of curve is it really following? Is it cubic equation? Is it polynomial, or even more higher order of cubic? Are there anything which you can combine with two different curves? One is before before it is taking the right speed. So those kind of things also required deep understanding of physics and mathematics. The third important part in this is also the computer science knowledge, which also helps us to organize things and data in the right way, making sure that the digital twin can deliver us the right value at the end. So these are basic ingredients which are required, or basic competencies that is required before we create the digital twin. But on the computer science, if we talk about digital twin, requires some sort of database. Now, database could be a structured text, a structured or unstructured database. For structured database, we can also use SQL. For unstructured database, we can also use NoSQL. These kind of two different languages are there, which can database retrieval methods are there that can be used. It can be hosted on premises or on the cloud. Database can also be in terms of Oracle database. If there is very large database, then it can be in MongoDB. And there are so many different database solutions are available in the market that can be used. Because data is very important. We also talk about, when we talk about database, we always think of a structured database, which actually gives data in a tabular form. But often these data also, some of the digital twin also requires data from social media. So Facebook or WhatsApp or even YouTube. So those kind of Twitter. So those kind of data, when it comes, it is highly unstructured. And then it can go into the data lake, where different processes are to be applied to make sure the data retrieval is in the right way, and then it can feed in to the algorithms. Now, when we talk about the algorithms preparation or the module preparation, so it is also advisable to not to create a very large single module where all the things are put together, but often required to create small modules which can talk to each other, and then it serves a very small process and supports the next processes or next modules. So those kind of modules we can create either in Python or R language or C++. Now these are so Python and R are the open source. C++ also we need to take the license. But there are also commercially available softwares like MATLAB Simulink or Altair. These are the different models, these are the different platforms on which we can create the small the modules which can talk to each other. Yeah. Python is normally used where the physics or the mathematical model is very much clearly defined. Then we use Python. It can also create the analysis on the statistical. However, the statistical libraries are very well defined in R language. So then people prefer, when there is statistical analysis, people also prefer R language. Yeah. So the modules that we prepare takes the data from these databases, processes, and sends back the output also in the database. Yeah. Also, as I said, when we go for the modular approach, one module has to talk to other module. Yeah. And even sometimes if we go on the site, let's say if I'm a service provider for airline, and I need to know that, okay, how is the weather forecast? Then I might actually create an API which actually connects with the weather.com and gets the data. So it's also like one module, which is weather.com, has the availability of the data, and then the other module which we have created on our premises, and then we link it with the API. Now API is nothing but application programming interface, and this is required for communication with different models. So there are different models of the API. So open API, internal API, partner API, composite API. And then there are different structures also. So the most favorable structure in today's time is REST API. And this is like the API which actually talks with certain rules, which is retransformational state kind of API, which actually creates the connect with the different programming methods. Now, such APIs are prepared on JSON, CSV, or XML database. So these are nothing but the languages that is used for creating the APIs. So JavaScript, that's the basic one, which is used for creating API. It's nothing but the data exchange. And then finally, somewhere it has to be represented. Otherwise, the user interface or user experience cannot be achieved. So then there are various modules available or various platforms available for creating user interface. So HTML is there, CSS is there, or JavaScript, Vue.js, Angular, Node, React and Node. So those are the different user interface modules are available, which can also create the right interface for user experience. Now, these are 4 different layers which are required to make sure the entire digital twin works in the right way. People can choose from different solution on the data or on the modules or on the API, and finally in the user experience, depending on the need. Yeah. So that's bit in a nutshell about what could happen onto digital twin in terms of tools and languages that we use. Last topic on the subject is mostly on the digital twin maturity model. So when we talk about digital twin, so it was started, as you have also seen in the video, around 20 years ago, in 2001 or so. Digital twin was a concept coined in and then was used by NASA for mimicking the their launched satellite launchers, that how it is going to perform in this space. But then industry have now started adapting it. So there has to be definitely a different maturity model, that to what extent an industry is adapting to Industry 4.0. So if I talk about the level 0, which is also coined by maturity model from Atkins or IT, it is level 0, which is the reality capture. So it is nothing but the photogrammetry or drones, use of drones or reality capture, yeah, like 3D, scanning of the parts. So 3D scanning of the parts. So this is the level 0 of the maturity model, and that is also known as a brownfield or existing or as-built system. Then most of the industry has also gone to level 1, where they created 2D map or system or 3D map, and then it is like the 3D model of the component. And today, even in the housing industry, if you see, the real walkthroughs are created and makes sure that before you get into the house, you can actually see the house in the virtual world. So those kind of things are already coined in by the industry, and they are extensively using it. So this is nothing but design or asset optimization or coordination. This helps a lot, making sure that before we manufacture something, we actually could see how it is going to be manufactured. The next level is, excuse me, yeah, next level is to also connect model with the data. Like I said on the performance curves. So when I create a model of one of the compressor, and then if I apply the mathematical model on it, I can see the simulation in terms of 4D, 5D, making sure that how the time is going to, so with respect to time, how things are going to change, with respect to sensitivity of one or other product, how it is going to change. Simple example, if there was only one variable, you know that it is just a line which can actually give us the right mimicking from the on the curve. But if I actually put the performance curve with which has got the 2 or 3 different parameters affecting, then it will go into the surface. So 3D surface will happen. But if the fourth dimension like time is added, then you will see that it will be changing over the time. So the surface also moves. So those kind of things, or mimics those kind of parameter based simulation happens in the maturity level 2. The third one is enriching with the real-time data set. So if the machines are fitted in with the IoT sensors, then these sensors can feed back data into the system and can tell us that how the machine is going to perform. Most of our cars today are also fitted with microprocessor chips, and then a lot of data is being transmitted to the servers of the automotive company, and this can also give us the right feedback that okay, what kind of automotive vehicles needs improvement into the industry. And those IoT sensors, the maturity what we gain will help us bring more operational efficiency. Yeah. The fourth is two-way data integration and interaction. So in case if the even from the remote or on cloud the data is or the system is updated, then it comes with also the two-way data integration. So we get the data back into the system, into the model-based engineering system, and then updated program is also fed back to the machine. Then it is the two-way data integration. So most of our mobile phones also have these kind of capability that the app is get updated over the time. So control the physical from the digital. That's where the maturity comes. And fifth, which is autonomous operation and maintenance. So here the complete system gets automated and or creates the signals that okay, there is a service need or there is intervention required from the service engineer. So those kind of systems are also in the maturity level 5. Different industries have different maturity model. Similarly, the Gartner's maturity model says only 3 levels. So 3D visualization and simulation, real-time monitoring, or analysis, prediction, and optimization. So different consultants have created different model. The most preferred one is Atkins model, where there is a maturity model of up to 5 level, which clearly distinguishes what is the right level. And even Electronics and Telecommunication Research Institute also has the 5 level, which is mirroring, monitoring, modeling, and simulation, federated or autonomous. The last thing on some of the numbers, when we talk about this industry in 2019, it was USD 3.8 billion. And it is predicted by 2025, it will be 35.8 billion, because everybody wants to take decision based on data, provided the data has to be right. And that means the data structure also needs to be defined in the right way, which provides single source of truth. Yeah. Some of the countries like UK, they have even developed policies using Gemini principles that, okay, if the digital twin has to be given, or where the one machine has to talk to other machine, then a lot of complications can arise, and to improvise on that, they have also defined that what could be the purpose, what could be the trust level, what could be the function. And then there is clear-cut guidelines defined to make sure the digital twin creates the right impact for Industry 4.0. With that, I end my presentation. Thank you for listening me on this digital twin project, and was happy to share the thoughts from my side. Over to you, Kavita madam.
Thank you so much, sir. Thank you so much, sir, for sharing your valuable insights, which helped us in understanding the real or virtual or actual applications of mathematics. Thank you for taking us on this journey from theory part of mathematics to its practical use in industries as well. How much mathematics is important in manufacturing, the manufacturing process of various equipments, and how you used the concepts of curve fitting, probability, and especially mathematical modeling for the same. And thank you for listing out the software skills also, which are useful for the same. And I am ascertained that the knowledge imparted by you will help all our faculty members to further spread these mathematical modeling techniques amongst our students also. Once again, I would like to extend a great thank you on behalf of our whole Department of Applied Science and Humanities of Parul University. Thank you so much, sir. Thank you.
Thank you, madam. It was great pleasure talking to you here, and look forward to have a similar engagement. Thank you.
You're most welcome, sir. Thank you so much.